Hey everyone, welcome back to Control Theory. Today we're going to be talking about transfer functions. They are incredibly cool, and this is going to be a great modeling example of how you're going to describe systems in this class. So previously we talked about Laplace transforms as a way of solving ordinary differential equations. Here, we are going to be taking systems and describing them as g of s or a transfer function. And this helps us to relate the manipulation of our controlled variable over our manipulated variable or disturbance variable. So in that, let's assume we have an inlet, which is our manipulated or disturbance variable called u of t. It goes into our model, and outside of that comes our controlled variable, which is y of t. In Laplace space, we can consider these as u of s going in and y of s coming out. Our transfer function then is going to be equal to our controlled variable over our manipulated or disturbance variable, which should seem pretty familiar based on the previous discussion that we had. We know that that would then be equal to the Laplace of our actual y of t or output control variable over the Laplace of our input or manipulated variable disturbance variable u of t. To take this into an application, we're going to walk back through in one of the previous lectures a liquid tank that we are filling. So we have Qi, which is our flow rate of material in. We have a changing height. We have a set volume in the tank at any height based on a cross-sectional area of the tank. And we have a flow rate of material out, Q. Using our material balance, we found that we had an accumulation term, which is the change of that height relative to a constant area. We had constant densities of everything, so we were able to take that out. And we were able to consider the inlet stream Qi and the outlet stream of Q. We related Q as a relationship of height over our resistance, RV, for simplicity. And this was really a factoring term of those areas and volumes, etc. We know a condition of H0 is going to be equal to H of the steady state. So we know that at the moment we're considering the system, we are already at a steady state value. But we need to be able to model what happens based on any type of disturbance or change in our inlet. Knowing that we're trying to control, in this case, the height, what are the relative changes that we need to make with respect to Q that might also be relative to disturbances in Qi? So taking that this was our set balance example, we relate everything in function of height as relationship to time. So the height's going to change over time. We can also consider, though, that over time, we might have changes in Q of I, which is our inlet stream. And of course, we can consider many different relationships. Maybe we have the ability to control Q of I, and we're trying to tune that as a relationship of height. But in that case, we might be considering that there's disturbances happening in Q. Maybe there's a blockage. So if we try and control Q, then maybe there's disturbances in Q of I. And these relationships are important for considering what ends up being the controlled or manipulated disturbance, but this kind of relationship of what's the numerator and the denominator will stay the same. And now remember, this now is n of s, our numerator term, and this is our denominator term, giving us the total expression for our transfer function. We have ways of solving that and determining coefficients and be able to use partial fractions for solutions, but now we can take this as our example. With that in mind, we're going to try and turn this into our standard system that we've been using. We did all the math to show that more or less, if we take these based on steady state conditions and then we also take them at a dynamic condition, more or less, we can get into a dynamic system. So we're going to write this in terms of things that can change and refer to them as our dynamics. Thus, ultimately, dH dt times A is equal to Q of I with disturbance minus our H disturbance over RV. And we know we have a condition that H of 0 is equal to H of steady state. That is a pretty set value for us. So if we wanted to solve this equation and we wanted to consider this as a transfer function first, we're going to need to do a Laplace on the entire system. So if we take the Laplace of the left-hand side, which is area times dH dt, will be equal to the Laplace of our right-hand side, Q of I minus H RV. Notice at this point, I'm just expressing this as the dynamic and just reflecting that it already has a function of time. So area is constant. We can pull this out of the expression, and we're taking the Laplace of dH dt. This is going to be equal to the Laplace of the entire right-hand side. This is truly the Laplace of Q of I minus the Laplace of this entire expression. R of V, though, is going to be a constant. So we can end up pulling that out of the expression. I'm going to leave it just for this second, but we will be able to extract that as well. And you can think of this as the additive rule, so we can really just add a negative 1 over R of V times the Laplace of our height function. In this way, we have the ability to use our table to directly solve for what these terms will end up becoming. So in this, we know that this area is going to now be multiplied by, let's turn this into Laplace space with a capital H, that will be S times H of S. And next, this will become a capital QI of S. This is going to already have pulled out of the expression and be multiplied by our capital H of S. We can solve base now to get a transfer function of our CV over our MV or DV, because we're trying to control, in this case, the height, and it's going to be a relationship to our other expressional term, which could be manipulated or disturbance, QI. We need to get G of S as a function of H of S over QI of S. To do that, we're going to move this to the right-hand side, and we're going to group the term together. So in adding this, we will get H of S times A times S plus, in this case, 1 over RV equal to QI of S. If we would like, we can go ahead and multiply everything by RV. The reason for why I'm choosing to do that is I want to get to a term that's just plus 1. It's a standard term that you're going to be seeing a lot in this class. So in doing that, we are going to be able to now get H of S times A times S times RV plus 1 equals RV QI of S. We can now divide this term to bring it over onto this side of the expression. We can also divide this term, and we will get our G of S is equal to H of S over QI of S, which is equal to RV over RV times A times S plus 1. This ends up being our model that describes the relationship of change in the Laplace space between our height, our output, and our input, which might be a manipulated or disturbance variable, QI. Now, notice that this is now a term that has a constant, S, and a plus 1. Ultimately, based on that, we are going to be able to perform an inverse Laplace on this system where we have our numerator expression and our denominator expression. But for right now in this part of the course, we're more interested in considering what are transfer functions, how can they be solved, and what kind of relationships then can we use in order to solve different systems of equation. We can use this to determine properties of transfer functions such as gains, orders, and see even different types of roots that may exist. So hopefully this is a great introduction for a second. I'm going to go ahead and erase the board so that we can walk through some more fun math and see what happens when we might have different conditions, such as many inlets or outlets. Now we're going to consider a system in which we might have multiple inputs. So let's say that we have a model and we have 2 inputs into our system. We have 1 output from our system. Let's say that our 2 inputs are considered to be based on functions x of t and z of t, where we have an output y of t. Now, if we move these into the Laplace space, these will end up becoming big X of s, z of s, and y of s. So if we are able to then describe this model based on the following ODE, perhaps tau dy dt plus y is equal to k1x plus k2z. And if we're able to use this ODE to describe this, let's consider a solution in which we're identifying transfer functions, and let's break this down a little bit. So Ta in this case is more likely than not going to represent our residence time, where the residence time here is more likely than not going to be a constant set value. We can also consider K1 and K2. Now, this can be based on resistances, this can be based on flow rates and volumes, it can be residence times of their own systems, potential inputs of gain for disturbance, but these are more commonly gains, and these are going to end up being constant as well. Thus, we really actually have to relate a couple of things. We have our two inputs, X and Z, and an output of Y. Our relationship here involves a differential and several of these that have a set constant in front, where we have ta times dy dt, a 1 times y, k1 ix, and k2 by z. So let's consider two different transfer functions that we might want to find. g1 of s we're going to refer to as y of s over x of s. g2 of s is going to be y of s over z of s. So how can we find this, and then how can we build out the full y function as a relationship of the full inputs? So output is equal to our inputs. Well, let's consider that all these are going to be in dynamic terms. And with that in mind, we are going to take this and apply a linearity rule directly. So on the Laplace of that by linearity, we're going to take the Laplace of the full expression. This is going to be ta dy dt plus y equals k1 times x, k2 times z. This is a constant that we can pull out of the expression, and dy dt from our table is going to directly become s times y of s. This term, Laplace based on our table as a y of t, becomes now y of s. This is going to become pulled out. K1 times the Laplace of x is going to be x of s, k2 times z of s accordingly. Now these are dynamic variables, so at steady state we do have a condition in which they're going to be 0, but based on that initial condition, we can consider these to be in dynamic terms. From the previous example and the current, I can right now just use them and write this above it, but we are really assuming that all these are going to be that way throughout the course at this point. So on that mindset, let's consider how we can turn this expression into transfer functions, those transfer functions that we have existing here. Notice that we're able to combine these y of s's into one term. So we have ta times s plus 1 all times y of s equals k1 x of s plus k2 z of s. And again, I'm just going to go ahead and use or not use the dynamic tilde accordingly. We could divide this by both sides and receive a return value of k1 over ta s plus 1 times x of s plus k2 over ta s plus 1 times z of s. And I want you to see something really interesting here. We are describing this now as our output in terms of specific inputs x and z, where each of these have their own transfer function that models their relationship between the output and the input. In reality, in order to get the specific transfer functions, one might now want to say, okay, well, let's bring in those initial conditions. We have initial conditions that perhaps when z of s is going to be equal to 0, well, what would happen? If z of s is equal to 0, then this term goes to 0, and we just have this term left. So in that case, y of s will be equal to k1 over ta s plus 1 times x of s at the condition that z of s is equal to 0. If we were to divide now this by that, we would get, funny enough, g1 of s, y of s over x of s equals k1 over ta s plus 1. Further, when we perform the opposite condition, that an initial x of s is equal to 0, this term will go to 0, leaving us with that. Y of s will be equal to k2 over ta s plus 1 times z of s at x of s equals 0. meaning g2 of s is y of s over now z of s, and it's equal to k2 over ta s plus 1. In reality, that means this term is g1 of s, and this term is g2 of s. So by shorthand, just in solving this, we actually can just look at this and say, oh, well, this is g1 of s because it's the relationship of that to this directly, as would this based on those alternate conditions. And furthermore, while you can just write this directly as the function now of y of s is equal to g1 of s, x of s plus g2 of s, z of s, that is true. But we can also see an interesting relationship here based on those initial conditions where now y of s is equal to y of s over x of s at z of s equals to 0 times x of s plus y of s over z of s when x of s is equal to 0 times z of s. And this should look a lot like your previous classes, such as when you took thermo and when you took differential equations. And I don't necessarily even need this term to be here. This is just for a conditional that we know that we've solved this previously to get that function. But in reality, we can even exclude that. And we're just looking at this, where those terms are going to cancel, that x of s over x of s, and that z of s over z of s, yielding y of s equals y of s based on the contribution of x plus y of s based on contribution of z. This should look the same as when you're describing your functions in thermodynamics to relate enthalpy and entropy and other thermodynamic factors. This should look like partial differential equations when you've taken those classes. Because remember, we're in Laplace space, so we're really describing the functional changes that are occurring. This is more or less your PDE and ODE solutions. This is how you would describe the total amount of change to an output based on relative changes of inputs. And this is so fascinating that even in Laplace space, we can get to the same solutional form. So we're going to just consider that this is how we would describe it for multiple inlets. And based on this, we're going to be able to consider multiple gain values, where again, these Ks are really gains. And we're going to see what happens with different conditions of gain and how we can approach different properties of transfer functions so that we can learn more about them and how we can use them and apply them in this course. We're going to talk about 6 different properties of transfer functions. I've written out 3 of them here so that we can walk through them. I'll erase the board and we can write out the other 3, and that will close out our functional expression about transfer functions for the day. So the 3 properties I'm first going to show you are steady state gain, order of a transfer function, and the gain time constant form. So when we're describing steady state gain, what we're really looking at is the fact that we can determine the steady state output changes based on a sustained input. So if gain is our functional term k, then k is going to be equal to the change from YSS at a second step point and YSS at a first step point, which are the steady states for both, based on the inputs that are happening between 1 and 2. So when we consider this and we have some input here and we have some output, we might have an initial steady state value of USS1 and a final one of USS2. Further, we are going to have some change in our output ultimately. So say that this is going to be some type of linear expression where we went up and we stepped up, we have this change here, delta USS. We're going to have some directed output change at that same time point that's going to lead to us getting to a new YSS. Ultimately, though, we do have a change of delta YSS here. So the amount of gain that we got is relative to how much of the difference of our output was based on the sustained input relating between the 2 steady state values that we eventually reached from our initial point t equals 0 to our second steady state value point when we finally reached it. And that could be determined as such, but it's important to note that if it's a linear process and a linear ODE, then k is going to be constant. Otherwise, for nonlinear, it may not be constant. So the question then becomes, how would you determine k directly from our transfer function g of s? And I've already given out the solution here that ultimately k is related to the limit of s equals 0 for g of s. But we've actually seen that before. It was the finite value theorem. And so in the finite value theorem, we saw a similar type of expression where we had the limit as t goes to infinity for some function y of t, and we described it as the limit as s goes to 0 for, you might have guessed, s times y of s, where we know that we can take this function and put it in the Laplace space and relate it as such. Now in this case, we know that g of s is going to be equal to y of s over u of s. So we know that y of s is equal to g of s times u of s in this case. And u of s here, we are going to be able to get based on a relationship of understanding what's happening in u itself. We know that delta USS right now, just based on our standard form, is equal to USS at time point 2 minus USS at time point 1. So what we're really looking at here is a step function. And if we took the Laplace of a step function that's happening here in this, that relates us from going from the first to the second one, for this specific example of a step function, we know that specifically that means that USS is going to be based on our step out S equal to total U of S. And now remember, this is based on the fact that we had the step function's Laplace is equal to 1 over s, and we know that the amount of actual dynamic change for this is delta USS. It's based on the final and the initial. Thus, that's where we would get US equals to this. Now we can plug that in directly here, and we can see what's going to happen next. So if we plug that into our expression, we get the limit as s goes to 0 for s times y of s, which is now going to be g of s, times u of s, which is going to be delta us over s. Those s terms cancel. We could pull out our uss term here, and that's going to become equal to the limit as t goes to infinity for y of t. Well, that's going to ultimately become the change of which we know to be true because y of s changing is going to be based on the relationship of the final minus the initial with these conditions. And so if the limit is true that this can go to infinity for y of t, then the relative change that's happened here is going to be delta yss on the left-hand side equals now the limit as s goes to 0 for delta uss times g of s. This is a constant that can be pulled out and divided onto that side, which would give us, now, funny enough, k, because it's equal to delta yss over delta uss times the limit, sorry, that's just directly equal, I divided that. So that's equal to, because of the division, the limit as s goes to 0 for g of s. So we know the gain itself in this kind of situation that we're describing here with the step function is this linear delta yss over delta uss based on relationship of time going to infinity for a function y of t, and that's equal to the limit of s going to 0 for g of s. This has to be true in the situations in which the finite value theorem is true. And so here, that would become our solution. In describing the second part, our order of a transfer function, what we're really looking at here is a representation that linear ODEs in the time domain can become polynomials in the Laplace space. So when we're going from t to s, what was a linear ODE can now become a standard polynomial. Now we've described this using our output over input or numerator over denominator functions. And before, when we were describing it in the previous lecture on Laplace, we used the sum of I going from 0 to m terms for b of I times s of I, where that's our coefficients b and s is our Laplace space. And that related to us on the numerator of b of m times s to the m plus b m minus 1, sm minus 1, and so on until we're finally down to b1 times s plus b0. We could do the exact same thing for our input functions, where we would have the sum from I to 0 to n terms for a coefficient times s to the I, and that's going to be related in the exact same way with our function. And now when we look at our Laplace transform table properties and we want to simplify this a little bit, we can notice that we have a lot of these terms that are, for example, the Laplace of some derivative function like d to the n for f over, I'm actually going to write this out here. I don't want to cover my face, but we will write it here as the Laplace for d to the n f's over dt to the n. That is going to become s to the n times f of s. And that'll be for any domain time function f, which is a function of t. And now, when we perform this, we can actually take this even in the reverse, now that we're in the Laplace space, and get right back onto that. But what we see is based on the relative number of n here for its ODE degree, that becomes the same order of our polynomial. So if it's the second derivative function we're taking, so d to the d squared f dt squared, that's going to become s to the 2 times f of s. So thus the order of the polynomial matters, and more, we're relating here the n order, which is the order of the transfer function itself based on the denominator. And that's really valuable to know. Further, it's an important property for us to consider that based on the top term, our numerator, we can discuss the dynamics of our system based on m. If m is greater than 0, then we know that the transfer function might have numerator dynamics. There's cases in which m is going to be equal to 0, but the numerator dynamics has a very strong effect on the total responsiveness of the system. We're going to see different types of examples of this, but for now, we're really considering that this is an nth order transfer function in total based on the denominator, based on that order that we have of our derivative in the time space, and that we could describe any type of time ODE that's linear as a direct polynomial in this space. When we move on to the third term, our gain time constant form, what we're really looking at here is that if a denominator polynomial can ultimately be factored into a product form like this, where it goes from 1 to n terms, pi meaning that we're multiplying, not adding as we would for some terms, for tis plus 1, then we might get our transfer function to ultimately look like still the output over the input, gain or k terms times b of s, which is our numerator term now, over these products, tis plus 1 times t2s plus 1 plus so on until tns plus 1, where again, n is going to ultimately be the order of our transfer function, but now we have this time constant that we've been considering. We know that this can also be true if bs satisfies the expression that the limit as s goes to 0 for bs equals 1. Meaning that this is ultimately going to be able to be factored for that type of denominator potentiated polynomial. Now what's really fun about this is actually kind of what we've been looking at. We've been noticing this kind of same trend, and that's why I keep saying let's try and create it to be something s plus 1. We want to be able to generate this kind of term for us to be able to describe the relationship between gain to time directly. Notice that the gain of our entire expression is now on top. This allows us to, in this form, to directly pick off the gain. We can pick off the time functions in our expression, and that will give us information about the speed of our system and other potential qualitative features of the dynamics that we're looking at in our total expression. So it's really interesting to see that these transfer functions that we're building, while they're always based off of the outputs and the inputs, have relationships about the speed or gain of our system, how we can factor these from one space to the other more quickly, and what kind of expression terms that we can pull out directly, such as our gain and our time functions, just based on how we rearrange and order the system itself. Now we're going to be able to continue with the last three of our properties for transfer functions. Property 4 states the physical realizability rule, which ultimately states that this rule of n must be greater than m. And these are based on the orders of our polynomials in the numerator and denominator. So the orders of our numerator m and our denominator n must be polynomials that have to be restricted by this due to physical considerations. And now this is actually saying what is really happening and how are we going to describe a real property using mathematics. Let's take a consideration on an opposite rule. Till now, we've been working on the rule that this value is true, but what if it's not true? Let's take n equals 0 and m equals 1, which means that for our output term y, we're going to consider the situation in which here we actually have n equals 0, meaning that there's no derivative orders. And there's a first derivative order here, m, that would be found here by our ODE. That means that when we create this in the Laplace space, we're going to have one coefficient value that's shown and not the other. So let's consider some functions here. Let's say that we have an input that's supposed to just be a step function, and that's it. So for an input that's a step function, we want to see what's modeled out in the y. And now ultimately, we want to see that this is based on the influence of just the step. So on an initial condition that at 0, 0, u becomes 0 from a steady state, and knowing that we're using a step function, let's perform the Laplace transform on this ODE. Taking it on the left-hand term, we have a0, our coefficient that's constant, multiplied by now y of s. The right-hand side, the first term of that, b1 times du dt. b1 is a constant coefficient that we can pull out of the expression, leaving us with s times u of s. We add that to the next term, bu, which is b times u of s. We can then factor out the u of s term from the right-hand side, yielding u of s times b1 times s plus b0. Now, we already described that the function of u is supposed to be a step function. And so now we're in Laplace space. How would u of t go when it performs Laplace on a step? That becomes 1 over s. So let's go ahead and substitute that term indirectly. The left-hand side remains the same, but the right-hand side, we've already factored out u of s, and that term is now just 1 over s. We multiply that by what we factored together, which was b1s plus b0, and let's go ahead and rearrange this equation a little bit. We're going to factor through our s terms, and we're going to divide both sides by a0. The left-hand side is now just y of s, and the right-hand side becomes coefficient term b1 over a0 times 1 plus b0 over a0 times 1 over s. If we perform an inverse Laplace to get back to time space and see how our output function looks, we would find b1 times a0 multiplied by the inverse Laplace of 1 gives us delta t, an impulse function. We add that now to the second term, b0 over a0 times the inverse Laplace of 1 over s is our step function. But we now have to consider that this is the reality of our output. We would have to model this as an impulse, which is an incredibly fast increase and then decrease. An impulse function looks like this, where at t equals 0, we have automatically this huge shift up and then it goes right back down. But we're also adding that with a step function at the same time. That's not physically realizable for this situation. Now, to be fair, impulse functions are very often not truly very realistic, but in the situation of adding both of these and knowing that we're actually coming from just a step function input, that doesn't necessarily make sense. Therefore, we're showing that this is definitely a true condition that we have to consider, and we're restricted by physical conditions. Next, we're going to walk through the additive property. We've actually walked through this a little bit. It was the beginning of today's lecture on transfer functions. So we're saying that we have outputs that might be able to be affected by multiple inputs. And the way of this is, let's say we have input u1 that is adding with input u2. Now, we can model these as transfer functions of g1 of s and g2 of s, and those are going to add together, shown here by this junction, yielding y of s. And we actually are showing here that we have this plus sign telling us that it's additive. These don't have to just be additive in terms of plus signs, they could be additive with negative signs, and that maybe y of s can be described as the addition of this but subtraction of this. And these are based on the models themselves, so telling us how the model is influencing the system and what we need to be doing with that, whether we're in the positive or negative region of our control. So when we describe this, we've already shown that y of s can be directly described then using these functions, where in that way we can say that y of s is equal to input 1 times transfer function 1 added to input 2, and transfer function 2. And we went through the description of how that works. Oh, I kind of look like Amazon here. As we go from A to Z for this, we can see the transfer function inputs are relative, where both of these correspond to their influence on y of s ultimately. And this does seem to be additive. But if this was a negative sign instead, then this would ultimately just become that subtracted. And that still works the same way, because we're adding both of them, but it's based on the subtraction of these, where that's yet a positive or negative term. And this becomes a lot more fun next for our multiplicative property, where this is going from parallel systems to a series system, which we've talked a lot about, like resistances. Now we're getting into parallel and series. This should all seem to be flowing from previous examples from CourseWiz. So we're describing the output based on the input, y2 of s based on u of s, but we're going to pass through multiple models. And we can take each of these systems to be true. So if we consider the first system, which is just going to be this junctional input, we have our output y of 2, which is going to be equal to our transfer function multiplied by what's going into the model. So that's going to be g2 times y1. And that's going to still follow these same rules of, remember, output and input relationships based on the transfer. But this is its own output. So that can actually be described by its own equation, where y of 1 of s is actually equal to g1 of s times u of s. So if we substitute that back in here, then we actually see that this is based on the g1 of s and u of s terms accordingly. And then we can use that directly to tell that y2 of s must be based on a multiplicative property with series of transfer functions g1 and g2 of how we've influenced u of s to become y1 of s and ultimately our final output y2 of s. So we can take all these conditions of transfer functions together and we can work with fun block diagrams. So let's say that we described one. What if we had a block diagram that was x of s going in to the first thing, g1 of s, and we also had z of s going into g2 of s. There's going to be add and subtract of these, telling you where they're coming in and out. And specifically, I meant to draw that up here, but add, we'll put it over here because we're actually talking about where on the junction it is. And out from it comes another g3 of s, yielding our final output y of s. How would we model y of s as a function of x of s and z of s, which likely will also now be modeled based on g1, g2, and g3? Well, let's go piece by piece and let's break this down and where it looks. So here, looking just at this part, we would have to consider the input into g3 and the output, which is y of s. Here, we would have its own input of x of s and some singular output. And here we'd have z of s going into an output. We'd also have a junction to consider for these points. So let's make up a quick term that we can just have for a second and then get rid of. We'll call this one alpha. This one we're going to call beta. This one we'll call gamma. And these relate lines that we haven't actually described yet. Well, we know that based on each of these, that when we consider this one in particular, that the output is equal to the transfer times the input, because the transfer is equal to output over input. Thus, y of s is equal to g3 of s times gamma of s, where gamma, again, is just a quick term they're throwing in there just to consider how it looks. We also know that here, alpha of s would be equal to g1 of s times x of s. And looking here, the same thing, beta of s is equal to g2 of s times z of s, where these are consistently our outputs are equal to transfer times input, the relationship of how much of the output is influenced by the addition. And now these can now be considered for this addition property here. And with that, we can actually model this entire thing together at the junction. To do that, we're just looking at the junction property, which is gamma of s is equal to alpha of s minus beta of s, We can substitute these terms in, and we would see that this is g1 of s, x of s, minus g2 of s, z of s, and that is our actual term here, gamma. We can substitute gamma s into our y of s function, and that would become g3 of s multiplied by gamma of s, which is g1 of s, x of s, minus g2 of s, z of s, and we could distribute our gamma 3, giving us, ultimately, g1 times g3. For space, I'm just going to, assume it's a function of s, times x, minus g2, g3, z. And that ultimately considers the situation of our overall transfer function that might have existed based on a relationship of x and z, where this would be our overall systems in the transfer function, overall transfer of x and of z. So the contributions of both of those, where we're considering that for the output change of y, all of the x input changes are based on their transfer functions that have gains that influence our y going up, and that z has influence of bringing it back down. And so together, we are able to effectively describe the relationship between x, z, and y as what's happening for each of these systems. So say that the gains are changing, let's say that the transfer functions are relative. This is going to be able to describe, based on all these terms together, how this ultimately would be modeled. And this is really interesting. This is really just adding and subtracting, it's multiplying. It is algebra that we are taking into consideration so that we can do some really impressive calculations. Now, this is in the Laplace space. We can then take this function back into the linear space with time, and we can see how this expression would look based on changes of our input values of x and z, and how that would affect our output y of s. So even if these were manipulated in disturbance variables, we can model how they work and how they directly influence y at all these points. So I hope that this has been fun and a great description about transfer functions, and I look forward to seeing you all next time. Thanks.